Let's look at problem 14 from OpenStax College Physics Chapter 28. How far does the muon in example 28.1 travel according to the earthbound observer? Here is example 28.1. So the example says, suppose a cosmic ray collides with a nucleus in the Earth's upper atmosphere, produces a muon that has a velocity v is 0.95 c. The muon then travels at constant velocity and lives 1.52 microseconds as measured in the muon's frame of reference. You can imagine this as the muon's internal clock. How long does the muon live as measured by the earthbound observer? So that's example 28.1 that they're referring to. And again, the first part asked, how far does the muon travel according to the earthbound observer? Then in part B, how far does it travel as viewed by an observer moving with it? And you're asked to base your calculation on its velocity relative to the Earth and the time it lives, so the proper time. And then in part C, we have to verify that these two distances are related through length contraction. Gamma is 3.2. So let's start out by writing our knowns and unknowns. And we start with the knowns in example 28. So we have velocity is 0.95 c, and the time that the muon lives measured in its own frame, so that is going to be the proper time, delta t naught, is 1.52 microseconds. And in example 28, we are asked to find how long the muon lives measured by an earthbound observer. So we know the proper time. That means that we're looking for the dilated time measured by the earthbound observer. Now, in problem 14, we're also told that gamma, which is 1 over square root 1 minus v squared over c squared, is 3.2. And then part A in this problem asks us to find how far the muon travels according to the earthbound observer. So we're looking for a length, and in part B, we're looking for how far it travels as viewed by an observer moving with it. So that's another length. So let's stop and think which lengths these refer to. So we are measuring the length that the muon travels, the distance the muon travels from the point of view of a lab on Earth. So that means that we are going to be measuring its proper length. So L naught is what we're looking for in part A, which leaves L, length contraction, for part B. And we are told to base these calculations for both L naught and L on the time, the proper time or the dilated time. And then in part C, we have to verify whether by doing parts A and B, L is going to be L naught divided by gamma, or L naught square root 1 minus v squared over c squared. So let's start out by solving for delta t, and I'm going to write it on the right here because that's from example 28. So delta t, the dilated time, is delta t naught divided by square root 1 minus v squared over c squared. So delta t naught is 1.52 microseconds, so we have to multiply this by 10 to the negative 6th, divided by square root of 1 minus 0.95 c divided by c is just 0.95, quantity squared. I don't have room for more, so that's why I'm writing it like that. So when we solve for delta t, when we plug all these numbers in, we end up with 4.87 microseconds. So that's what the example in example 28.1 was solving for, this delta t. Now in problem 14, we're looking for other things. We want L naught and L. So L naught is going to be distance times velocity. Sorry, it's going to be time times velocity. So it's some sort of delta t times the velocity of the mu1. And we have to remember that in the frame of Earth, so the observer from Earth measures the proper length but dilated time. So we have to use L naught and delta t here. And then later on, when we're going to solve for L is measured, so the contracted length is measured by the mu1 as it's traveling. And the mu1 that's traveling actually measures the proper time, but the contracted length. So the equations are L naught is delta t times V, or L is delta t naught times V. So now we're plugging in the numbers that we have. So delta t was 4.87 microseconds converted to seconds, and the velocity is 0.95 c. And when we multiply these together, we end up with 1.39 kilometers. Then in part B, we're measuring for length contraction. So L is delta t naught, which is the proper time. So that is 1.52 microseconds times the velocity, which was 0.95 c. Plugging these numbers in, we end up with 433 meters. So now we know that the proper length is larger than the contracted length, and that's a good thing. That's what we would expect. And we have to check the relationship between them and see if indeed we get the gamma. So if I'm going to divide L naught by L, I get 1.39 kilometers divided by 433 meters. So that will be approximately 3.2, which was given to us as gamma. So we did the problem correctly. We have the correct relationship between length, contraction, and the proper length.